haven't actually said the power rule. I'm just helping us to use our powers of observation here to give a couple of examples. And now for a really ugly one that is probably all it's going to take for us to have that power rule memorized. So if I told you that g of x was equal to 10x to the fourth plus 5x cubed minus 3x to the negative third plus 7x squared minus 2x plus 5. And we had to take the derivative of this. The power rule in a nutshell says take the coefficient on x, bring it down in front. Sorry, take the power on x, bring it down in front, multiply it by the coefficient. So I'd have 4 times 10, which would give me 40, and subtract 1 from the exponent. I'd have an x cubed. That 5x cubed, I'm going to take that 3, bring it down in front, and multiply by the coefficient. So 3 times 5 is 15. Subtract 1 from the exponent. I'm going to take that power, that negative 3, bring it down in front, and multiply it by that other negative 3. It's going to leave me with a positive 9. And then I'm going to subtract 1 from the exponent. So negative 3 minus 1 gives me a negative 4. 7 times 2 puts me at 14. Subtract 1 from the exponent. This part at the end, this negative 2x plus 5, it is both the most straightforward and most confusing part of the power rule. A couple of different ways to think about this. If this were the entire function, that's the equation of a line. Y equals negative 2x plus 5. And if the whole idea behind the derivative is to find the slope, we know where to find the slope of that line. It's just the coefficient on x. So the slope of negative 2x plus 5 by itself is negative 2. Now, if you want to follow the power rule, then in terms of what's happening for the power rule, it is important to note that x to the 0 is equal to 1 as long as x is a number. Infinity to the 0 gets weird, but a number to the 0 power is 1. So if you really, really, really want to make this the power rule, I am looking at x to the 1. 1 times negative 2 is negative 2. And then technically, right, I'd have an x to the 0, and x to the 0 is equal to 1. And if you kind of thought about doing that with a 5, I could think about that as saying 5x to the 0. And then when you bring down the exponent, 0 times a number is just 0. I do not recommend thinking about it that way. I truly think that when you see something linear, we just know how to already find that slope. And when we take the derivative of a constant, it's going to be 0. And again, if I think about that graphically, if I had the function y equals 5, well, what that looks like is a horizontal line at y equals 5. Well, what's the slope of a horizontal line? That slope is 0 everywhere. So I think that when it comes down to a number times x or just a number, I don't think about the power rule. I'm really thinking about what does it mean to look at the slope. Questions about the power rule before we get messy? Cool, let's get messy. Let's see. So, so a question, do you put 0 for the derivative of a linear function? No. You would put 0 for the derivative of a constant. But if I had y is equal to 3x minus 5, and I just asked you for the slope of that line, go ahead and put in the chat, what's the slope of this line? Everyone can play along. Totally. I got a couple people telling me 3. That's the slope of that line. So what I'm saying is if your function is linear, you already know how to find the slope. We're just going to look for the coefficient on x. But if my function is a constant, the slope of a constant is 0. So if this is your first time encountering derivatives, you might do something like this. If my f of x looks like 7x plus 5, I might think about this as my derivative looking like, well, I know if it's 7x, the coefficient on x is the slope. And I know if it's 5, the slope is 0. Just to help reinforce that when we have a constant, the derivative is 0. If I have a constant times x, the derivative is the constant itself, or the coefficient. Dun, dun, dun. Okay, let's do some messier examples. If from a previous life, you know about product and quotient rule, awesome. We're going to get there on Thursday. Or maybe today if someone really, really needs to, but there's a lot that we can do with just the power rule. So if my function looked like, I'm going to make it gross. The square root of x plus 3x to the negative 4th minus 5x squared all over x cubed. And I asked you to find the derivative. First of all, we are not doing this with limit definition of the derivative. It's way too gross, and we're only going to use that if the problem tells us that we need to use the limit definition of the derivative. Other than that, we're thinking shortcuts. So really what I'm hoping is that we can turn this whole thing into a number times x raised to a number. The first thing that I'm going to look at is I just have one term in the denominator. And that means that I can break this apart to be 3 separate fractions, which is going to help us move towards something that looks like a number times x raised to a number. Breaking that apart into 3 fractions and thinking power rule. So I have to write things with powers. Square root of x is going to become x to the 1/2. I'm going to put that over x cubed. My next term, I've got 3x to the negative 4th, also over x cubed, minus 5x squared all over x cubed. Oh, that's not my derivative yet. All I was doing was some algebra. So I need to make sure that notation-wise, I'm still writing that as the function itself. Next up, I'm going to use exponent rules. Still not taking a derivative, just using exponent rules. Thinking about those exponent rules, I know that if I'm dividing 2 things with the same base, I get to subtract the exponents. So 1/2 minus 3. And if you prefer decimals, it's okay to write this in decimals. It's generally not the way you're going to see things written in the notes or written in the back of the book, but you won't be wrong if you prefer decimals. I'm going to stick with fractions. So 1/2 minus 3, and if I kind of come off to the side to think about this, I'll multiply my 3 by 2 over 2. That means I'm looking at 1 minus 6, or negative 5/2. So I've got x to the negative 5/2 plus 3x to the negative 4 minus 3 is going to give me negative 7. And 2 minus 3 is going to leave me with negative 1. Now that every term is a number times x raised to a number, I'm ready to go ahead and take the derivative. Using that power rule, grab the power, multiply it by the coefficient out in front, and then subtract 1 from the exponent. And just remember that when you're subtracting fractions, subtracting 1 is really like 2 over 2 or 3 over 3 or 4 over 4. So if I subtract 2 over 2, I'm at negative 7 halves. 3 times negative 7 is going to leave me with negative 21. Subtracting 1 from that exponent is going to put me at negative 8. And minus a minus will make that a plus 5x. Negative 1 minus 1 is negative 2. Good times. Also, if you're doing web work homework, just be super careful when you've got fraction exponents to go ahead and put that in parentheses to make sure that the whole thing gets captured as an exponent. Just like this function is not defined when x equals 0 because we have a vertical asymptote, we also don't have a slope defined there. So if I think about as I'm coming, I don't have a slope defined there because I couldn't find a single tangent line kind of to both parts of the graph. Another place where my derivative is not defined at a point, and that's what he was talking about in class in terms of having specific values where my derivative is not defined. If I think about something as simple as y equals the absolute value of x, this does have a derivative defined. There is a slope everywhere except for this sharp point at the bottom. Now, the reason that we have a slope everywhere except for that sharp point at the bottom, if I think about breaking this apart, and this is always going to be our trick for absolute values in calculus, that when I have an absolute value, we're really breaking this apart as a piecewise function. When x is positive, we don't have to do anything to that piecewise function. But when x is negative, we know that taking the absolute value flips the sign, meaning this would look like negative x. Well, if I think about that, on this side, if my line is y equals x, then we know what the slope is. That slope is positive 1. If my line is y equals negative x, over here on this side, we know what the slope is. That means my slope is negative 1. So at that point where x equals 0, my function is defined there. Absolute value of 0 is 0, but my derivative is not, because I'm instantaneously going from a slope of negative 1 to a slope of positive 1. So that's really what he was trying to get at in terms of functions where the derivative is not defined. It isn't that it's not defined for the function. It's just that it might not be defined at a particular value of the function. And here are the two most common ways that happens, either because secretly the thing could be written as piecewise, or where we have vertical asymptotes. I claim that there are only 3 points on that graph where I am completely sure that I know what the slope of the tangent line would be. And those are the 3 places on the graph where the curve kind of levels out, these flat spots. So I know that at each of those 3 points, the slope at that point should be 0. Now, at other points on the graph, we can probably estimate what the slope might look like. We won't be able to do it super accurately, but we can get a good estimate of what the slope is. So thinking about right here, whatever that slope is, it's some kind of positive value, because as I move from left to right on the graph, my y values are getting bigger. They're going up. So I know that right here, I should have a positive slope. Now up here, it's also a positive slope, but it's kind of flattening out a little bit because we're getting closer to that slope of 0. But on the other side of 0, now my slopes are negative because my graph is kind of going down. If I think about roller coasterology, that's not a word, but if I think about this in terms of roller coasterology, like I'm riding a roller coaster here, I'm going down, and then I was going up, and then I'm going down again, and then I'm going up. So in those places where we're going down, I know that those slopes are going to have negative values. And in the places where we're going up, I know my slopes are going to have positive values. So I've got positive slopes happening over here. I've got negative slopes happening over here. Positive slopes happening again. So if I were to think about, instead of graphing that function, but I actually wanted to graph the slope, then I know that a graph of the slope should be 0 at negative pi over 2, at pi over 2, and 3 pi over 2. And I know that everywhere between an x value of negative pi over 2 and positive pi over 2, these slopes are all positive. So whatever else is happening on my graph, it's got to be up here somewhere. And in this window from pi over 2 to 3 pi over 2, all of these slopes are negative. So whatever else is happening on the graph, it's got to be down here in this window where we'd have negative values for the slope. Here's the part where I'm waving my hands a little bit. If I had graphed this better so that we could actually estimate the slopes of these tangent lines, I claim that this spot right here, it's the steepest slope that we're going to hit on the graph. So when x equals 0, we're going to be at our largest positive slope. Between x equals 0 and pi over 2, these are positive slopes, but they have to be going from that maximum value down towards the slope of 0. On the other side of the curve, because this thing's like perfectly symmetric and replicates itself, right there, that's my steepest negative slope. And our steepest negative slope is going to represent the lowest possible value that we're hitting in terms of the slope. And again, in here, my slopes are all negative, but they're kind of going from 0 to our lowest negative value. After we hit that lowest negative value, these slopes are negative, but they've got to get back up to a slope of 0. So these are kind of headed back up to that slope of 0. And then because this repeats itself, the slope here at 2 pi ought to be the same as the slope we had at 0. So even if I don't know what the value is, I know that it should be the same. And this ought to be looking like a pretty familiar graph to you. Turns out this is, in fact, cosine of x. And we can also use limits and trig identities to show that, in fact, the limit definition of the derivative of sine of x will lead us to cosine of x. And that's in the book, if anybody really wants to take a look at it. For our purposes today, what I really want to get us started on is memorizing those trig derivatives. Now, there's another notation for the derivative, which is d by dx or d dx. And when I write this and put something in parentheses, this says the derivative of sine of x. It's just a different way of putting the notation. And the derivative of sine of x is cosine of x. The derivative of cosine of x, you might guess a sine of x, which would be close, but wrong. It's actually negative sine of x. We're going to add all 6 of our trig derivatives eventually, but for right now, you can get started on memorizing those trig derivatives And I'm just going to let you know, you need the trig derivatives in 17a, you need them in 17b, and you're still going to need them in 17c if you need all 3/4.